Hello everyone, welcome to our course Introduction to Basics in Veterinary Diagnostic Imaging. Today we will learn about the radiographic qualities and factors affecting the qualities. We will be learning about the definitions, the different parameters that define the quality of the radiographs and the factors affecting the quality of radiographs. Starting with the introduction, radiographic quality refers to the accuracy with which anatomical structures of the part being radiographed are represented on a radiograph. In general, if visibility and sharpness of the structures is good, radiograph is defined to be having a good quality. It is important to understand the factors which is essential to obtain a good quality radiograph. The three visual requirements of a good diagnostic radiographs are excellent detail, correct density and proper scale of contrast. If you see the radiograph on the right side of the screen, you can see a very good quality in the radiograph where you have got an excellent detail, it has got an optimum density as well as it has got a proper scale of contrast. So let us go one by one. What do you mean by the radiographic detail? It is nothing but the degree of sharpness or the definition of an object on a radiograph. Detail is good if structural and contour lines of the objects are sharp. If you can see here on the radiograph, we are able to define the outline of the bones very clearly. We can outline we can have the outline of the gas bubbles inside the abdominal cavity, inside the intestines. You can see on the radiograph on the bottom, you can see the fecal matter filled in, which has a very good sharpness inside. So with respect to detail, these radiographs can be considered to be having a very good detail. What are the factors that affect the details, the radiographic details? The first one is the geometric factors, intensifying screens, motion of the patient, film and X-ray tube, differential absorption of X-rays, double emulsion of the film, radiographic motile, exposure factors used, film processing technique, and the scatter radiation and the fog. So there are different factors that affect the details, which is going to have an effect on the outline of that particular structure, what we are going to see. And let us see one by one. What are the geometric factors that affects the radiographic detail? The major limitation of radiographic imaging is that the images are two-dimensional, although the patient is three-dimensional, which means that we are going to take a radiograph or we are going to make an image on the radiograph of an object which is having a two-dimensional structure. So we are going to make it into a two-dimensional structure. So we are compromising somewhere by making the image compress in one direction, from up to down or lateral to medial. We are going to make it compressed. So we are going to miss a lot of details when we are going to make a 3D structure into a 2D image. And what are the consequences of radiographs being two-dimensional? The consequences are, it causes magnification and distortion. It produces an unfamiliar image of a familiar part. There can be loss of volumetric perception. There can be superimposition. What do you mean by this magnification? When we were learning about the basic principles of taking the radiograph, making a quality radiograph, we told like the part film distance and the film focal distance should be maintained properly. The part film distance should be somewhere around, should be 0 centimeters, while the film focal distance shall be somewhere between 90 to 100 centimeters. So when we talk about the part film distance, it is which we say like it should be 0 centimeters, but practically it is not going to be possible, which means that we are going to see some kind of magnification on that particular organ on the image. So what this magnification defines is, it is the enlargement of a structure in the image relative to its actual size. So since we do not have a 100% or a 0 centimeter PFD of a particular structure, because of the structure being a 3D structure, there can be a small amount of magnification, and that magnification will increase as this 3D, the size of the 3D structure is going to be much bigger. The next one is the distortion, and this distortion happens, distortion means it is the unequal magnification, and this happens due to the object and the receiver if they are not on parallel to each other, which means that the object and the receiver and the film should be parallel to each other. It shall not be in a slanting direction. If it is going to be in a slanting direction, we are going to have an unequal magnification of a structure which is of similar size. Next one is imaging of a familiar part appearing to be unfamiliar, and this usually happens because of improper positioning of the patient. Due to the entire patient which is not oriented properly in a standard manner with respect to the receiver, then in such situations we get to see an unfamiliar structure on the radiograph, which is not equivalent to a familiar part. The third geometric factor is the loss of the volumetric perception. As we told before, we are making an image of a 3D structure. We are making a 3D structure into a 2D image, where we are going to miss a lot of information with respect to its thickness. So, but still we are taking a radiograph and we need some information on all the sides of that particular organ. For that reason, we are supposed to take at least 2 different projections. That too, it shall be at 90 degrees to each other. So that those projections are called as the orthogonal views. So always make sure that to avoid this loss of volumetric perception, always make sure that an orthogonal views are being taken. The next one is superimposition. The superimposition is nothing but when one structure is superimposed on another, and which can create an obvious opacity that can be misinterpreted as disease. So there are different organs in a single plane itself while when the x-rays are passing, and these organs can superimpose each other and we may misinterpret to be some kind of abnormality. So these are the geometric factors which can affect the details of a radiograph. The next factor is the motion factor. It can be with respect to the screen, with respect to the patient, or with respect to the x-ray tube. If there is a motion on any of these portion or on any of these parts or all the parts, we are going to get a poor detailed radiograph. The motion can cause a blurring of the image on the radiograph, by which the image becomes not suitable for any kind of diagnosis. So how can we address this? It can be addressed by placing the screen on a flat surface. It shall not move. The patient shall be restrained properly so that the patient will not move, and the X-ray tube, that it shall also be kept static without any movement. The next factor is double emulsion of the film. Since films are coated with film emulsions on both the sides, an image is formed on both sides separated by the base of the film, and this is going to cause unsharpness of the image. So when we were learning about the films, we told like the film is having a gelatin outer coating. Underneath that we get emulsion, underneath that we get an adhesive, and which is all placed on a base, and it is present on both the sides. So this emulsion has got the silver halides in it. So the images, whatever is going to come, is going to be formed on this emulsion portion of the film. And since these emulsion layers are present on both the sides, we are going to get image formed on both the sides, and which means that we are going to have two different images of a single projection on the film, and these two images are going to get superimposed, and these two images formed on both the sides of the emulsions is going to cause an unsharpness of the image. But this parallel unsharpness is actually would be very negligible, and may not be usually affecting the detail of the radiograph in a larger volume. The next factor is the radiographic motility. It is nothing but the appearance of non-uniform densities on a radiograph, causing loss of detail, which is called as a radiographic motile. And it may be due to the intensifying screens, or may be due to the film graininess. There are two types of radiographic motility. The first one is called as the screen motile, and the second one is called as the graininess. In screen motile, it has got two different screen motiles. One is called as the quantum screen motile, and the second one is called as a structural screen motile. In quantum screen motile, what it is due to the fluctuation in the absorption of X-ray photons exposing the film, while the structural screen motile is due to unevenness in the thickness of phosphor layer of the screen and imperfections in the crystal size. While the graininess, it is due to random distribution of silver grains in the film emulsion, and is visible only when the radiographs are examined under magnifications. So radiographic motile is also a factor that affect the radiographic detail. The next one is the exposure factors. The exposure factors, which include the kilovoltage, the milliamperage, and the seconds, and the time. So these three are the exposure factors. When we are going to have an X-ray which is underexposed or overexposed, it can either form a too light radiograph or a too dark radiograph, which is going to lead to loss of the detail of the radiograph, which is going to be of no use for the diagnostic purpose. So we have to fix this parameters or the exposure factors optimum for that particular animal, for that particular area that is being radiographed. According to the thickness, it has to be decided and fixed. The next is film processing. The correct processing of the film is absolutely necessary to obtain a good quality radiograph, and the processing errors can cause loss of radiographic detail. So the next factor is the scatter radiation and fog. Both the radiation, scatter radiation as well as fog, they reduces the radiographic detail. The next parameter is the radiographic density. What do you mean by this radiographic density? It is the measure of the degree of blackness on a processed film and is directly related to the number of X-rays reaching the film. So which means that uh, more the number of X-rays that reach the film, the radiograph is going to become more darker or more blacker, and such a radiograph will be classified as such a density will be classified as a high radiographic density. We are going to see the blackness on the radiograph, and it is all depending upon the number of X-rays that have reached the film. And this density is influenced by the subject density and its thickness, while the subject density is nothing but the weight per volume of the subject, and the radiographic density is inversely proportional to the subject density, which means that when a denser subject is there, I'm going to get less density on the radiograph. It is going to attenuate the X-ray photons, and only few X-ray photons are going to reach the cassette. Those objects which allow X-rays to readily pass through them appear blacker on the film and are radiolucent. And those which inhibit most X-rays appear whiter and are radio opaque. What are the factors that affect the radiographic density? The first one is milliamperage, exposure time, kilovoltage, film focal distance, speed of the film and the intensifying screens, developing time and temperature, and the grid ratio. Milliamperage. It is one of the major factors that influences the radiographic density. The milliamperage, as it increases, it produces more X-rays and they are going to reach the film. And the radiographic density is directly proportional to the milliamperage, provided that all other factors remain constant. The next is the exposure time. The radiographic density is directly proportional to the exposure time if all other factors remain constant, as total production of X-rays is increased, which means that when the time is increased, the number of X-ray photons that are being produced is going to be huge in number, and those X-ray photons which are going to hit the cassette or the receiver is going to get increased, and we are going to get a more dense radiograph. The next one is kilovoltage. Kilovoltage controls the quality of the X-rays. A higher kilovoltage produces high energy X-rays with high penetrability, and radiographic intensity increases with increase in kilovoltage, which means that when I'm going to have a higher kilovoltage settings on my machine, I'm going to produce high quality X-ray photons with high energy. When high energy X-ray photons are being thrown out from the X-ray tubes onto the patient and then to the cassette, it is going to penetrate completely, or more number of X-rays are going to get penetrated through the body cavity, through the body part, and it is going to hit the cassette or the receiver. And if more number of X-ray photons are going to reach on the cassette, I'm going to get a more dense radiograph. The next one is the film focal distance. Due to a film focal distance change, variations in density are inversely proportional to the square of the distances. And if the film focal density is reduced to half of the original distance, the radiographic density will increase by a factor of 4. This shall always be kept in mind, not only with respect to the production of a quality radiograph, but also with respect to the protection of the staffs standing inside the room. When we move twice the side, I'm going to have, if I'm going to make the distance more, I'm going to have a fourfold increase in the X-rays hitting on the people surrounding. So let us talk about the film density. If the film focal distance is reduced to half, the density is going to get increased by fourfold. So which means that I have to keep it at the optimum to make the density of the radiograph correct. And for that reason, the optimum FFD for to be used in veterinary science is somewhere around 90 to 100 centimeters. Next is the developing time and the temperature. Overdeveloping of the films as a result of increase in time and or temperature of the developing can lead to increase in radiographic density. So I shall not keep my films inside the developing solution or the fixing solution for a longer period. That can lead to an increase in density. I shall not increase the temperature. I shall maintain the temperature of the solutions in the proper way, so that I can have a good dense radiograph. The next is grid ratio. The higher the grid ratio, higher grid ratio allows more absorption of scatter radiation to affect the radiographic density. The next parameter is the radiographic contrast. The difference in various densities of adjacent areas on a radiograph is called as a radiograph contrast, which means that I should be able to, if I am having a radiograph in my hand, and if I am searching for certain I am observing it and for an interpretation of the radiograph, I shall make sure that I am able to identify between the structures which are lying together or which are lying side by side. It appears as a difference between blackness, grayness and whiteness due to variations in subject densities, and enables the radiologist to interpret diagnostic information contained on a radiograph. The radiographic contrast is the product of film contrast and the subject contrast. And the subject contrast is the difference in the relative densities of various anatomical structures of a particular subject. The contrast can be a low or a long scale contrast, or a high or a short scale contrast. An image, if I am having many densities in that radiograph, I call it as a low contrast or a long contrast scale, while if I am just having 2 or 3 contrast in my radiograph, I shall keep it like high or short scale contrast. And for a radiologist, he should be always thinking about, or he should be always looking for a long scale contrast in front of him, so that he can identify each structure separately to have a proper diagnosis. A good radiograph is expected to have a long scale contrast, so that details of the different structures are well visualized. What are the factors that affect the contrast? First one is the thickness of the part. Second one is the density of the part, effective atomic number of tissue, kilovoltage, and fog and scatter radiation. Thickness of the part. Intensity of the transmitted beam is inversely proportional to the thickness of a given part. And if thickness is increased, the transmitted X-ray photons are reduced. So when the thickness is increasing, the attenuation is more, and the X-ray photons are going to get reduced, which are going to pass through that particular portion. Next is the density. The greater the density of a tissue, greater is the ability of the tissue to attenuate the X-ray beam, and the radiographic density is inversely proportional to the subject density. So thickness and density are all inversely proportional to the subject density. Next is the effective atomic number. The attenuation of the X-ray beam by photoelectric absorption is increased in substances with high effective number. The difference in the effective atomic number of tissues is an important factor that influences the contrast, and difference is high between bone and muscles. So we get a very good contrast if we view an radiograph where there is presence of bone and muscles together. And it is the same principle by which contrast radiography also works. We are going to have either a positive contrast agent or a negative contrast agent, which is going to define the other structures, make it different by changing the contrast. The next one is the fog and the scatter radiation. The film fog, due to light leakage in the cassette or due to processing errors, reduces contrast. And similarly, the scatter radiation reaching the film, they produces undesirable densities which cause loss of radiographic contrast. Kilovoltage, it is the ability of the X-rays to penetrate through a thickness of tissues, which depends upon the energy of the X-rays, which in turn is dependent upon the kilovoltage applied. The higher kilovoltage, it produces a high energy X-ray photons, which has got shorter wavelength and higher penetrability. As a result, there is a little variation in the penetration of thick and thin tissues. This results in low or long scale of contrast. At lower kVp, the lower energy X-rays are generated, which pass through thin tissues but fail to penetrate the thicker tissues. Thus, high and short scale contrast is obtained, and the radiographic contrast, it varies inversely with the kilovoltage. The various tissues and substances, according to the radiographic opacity produced, they produce various types of opacities, like the air or the gas. They might be looking dark on a radiograph, and that can be due to any gas collection present in the body. Fat, it can be more towards the darker side, and it can be due to any tissue that is composed mainly of fat. Water and the soft tissue has a similar opacity, and this would be more towards whitish in color, and this can be due to presence of any fluid or presence of soft tissues like muscle or the internal organs. The fourth one is the bone or the mineral opacity, and this is usually due to the mineralized region. This can be seen on bones. This can be seen the skeletal bones, or this can be seen in radiographs which of animals which has consumed certain bony pieces. And the next one is metal, which would be looking much very bright on a radiograph, and this can be due to anything that contain a metal. Thank you. Here ends this class.